Something is physically blocking the jet stream over the Atlantic Ocean right now, and the thing doing the blocking is not in the sky at all. It is sitting underwater in a patch of ocean that has been quietly cooling for more than a century while everything around it warms. Meteorologists have started calling out this exact patch by name when they explain why entire continents keep getting stuck under the same weather for weeks at a time. And the more scientists study it, the more they are realizing this is not a local curiosity confined to the North Atlantic. It is reaching into monsoon systems on the other side of the planet, reshaping flood risk across southern Europe, and doing it all through one surprisingly simple physical mechanism: temperature contrast in the water pushing around one of the most powerful wind currents on Earth. The patch is officially called the North Atlantic Cold Blob, sitting in the ocean south of Greenland and Iceland. Since the year 1900, this specific stretch of water has cooled by roughly 9/10 of a degree Celsius, even as the rest of the planet's oceans have warmed substantially over the same period. That kind of contrast does not happen by accident, and scientists have spent years arguing over exactly what is causing it. The debate has mostly settled around two competing explanations. One camp argues the cooling comes from local atmospheric effects, changes in wind patterns or cloud cover that increase heat loss directly from the ocean surface. The other camp, backed by newer and more direct evidence, argues the cause runs much deeper, literally, tied to a slowdown in the Atlantic meridional overturning circulation, the vast system of currents that normally carries warm water north from the tropics and delivers it to this exact region. New research published this year has pushed that debate meaningfully in one direction. A team led by Stefan Rahmstorf at the Potsdam Institute for Climate Impact Research analyzed roughly 70 years of observational data and found the cold blob is best explained by reduced ocean heat transport rather than increased surface heat loss. In plain terms, less warm water is arriving in this region than used to arrive, not because the local air is stealing more heat away, but because the ocean current bringing that heat north in the first place has weakened. The team describes this as the most direct observational evidence, yet confirming the cold blob functions as a distress signal for a slowing AMOC, and their published projections estimate the circulation could weaken by as much as 51% by the year 2100 if current trends continue. If you're finding this as unsettling as I did digging into it, do me a favor and hit that like button. It genuinely helps this channel grow. Understanding why a slowdown in ocean currents translates into a blocked jet stream requires walking through the physical chain step by step, because each link matters. The jet stream is a fast-moving river of air, flowing generally west to east across the North Atlantic, and it acts as a steering mechanism for the weather systems traveling beneath it. Under normal conditions, it flows in a relatively smooth, direct path. But the jet stream is extremely sensitive to temperature differences in the air beneath it, because those differences in surface temperature translate directly into differences in air pressure and air density above them. When a large, persistent patch of unusually cold water sits directly beside a patch of much warmer water, the boundary between the two creates an unusually sharp temperature gradient. Ocean physicist Marilena Oltmans at the University of Bremen has described the resulting cold front as acting like a guide, physically bending the jet stream and forcing it to loop northward around Europe instead of crossing directly over the continent. That bending is the entire mechanism behind the blocking. Instead of a straight, fast-moving jet stream sweeping weather systems along on a normal schedule, the current becomes wavier and considerably slower, prone to getting stuck in large looping patterns rather than flowing smoothly past. When the jet stream loops northward and stalls in that position, it leaves a gap beneath it where high pressure can move in and simply sit, undisturbed for days or weeks at a time. Meteorologists call this a blocking pattern. And it is precisely the mechanism behind the heat dome that baked Europe through its third major extreme heat event of this year, with temperatures touching 44 degrees Celsius in France alone. Researchers studying this exact sequence of events have identified something they call the salinity to storm mechanism, a chain reaction that appears to repeat with striking predictability from year to year. It begins with meltwater and runoff pouring into the subpolar North Atlantic, creating a shallow layer of less salty water, sitting on top of the denser, saltier ocean beneath it. Because this fresher surface layer is less dense and more isolated from the water below it, it cools far more rapidly during the winter months, sharpening the temperature boundary that eventually disrupts the jet stream the following summer. That sharper winter boundary fuels stronger storms, which generate powerful westerly winds capable current further north than it would normally travel. By the time summer arrives, that displaced pocket of warm water sits in an unusual position, acting as a physical barrier that deflects the jet stream and clears the way for high-pressure heat domes and drought conditions to settle over the continent for extended stretches. If this kind of deep science content is something you want more of, make sure you subscribe, because there's a lot more of this coming. The consequences of this blocking pattern are not limited to prolonged heat. In a strange twist, the same disrupted jet stream capable of trapping heat over one part of Europe can simultaneously push dangerously cold air masses further south than usual in other regions. As the traditional Atlantic circulation weakens and the upper atmosphere grows less stable, pockets of cold air are increasingly likely to detach and sink to lower levels far from where they originated. Meteorologists in Spain track this phenomenon closely under the name depresiones aisladas en niveles altos, or cut-off lows, systems that form when a cold air pocket separates from the main jet stream and drifts independently. When one of these cut-off lows interacts with an increasingly warm Mediterranean Sea, it can dramatically intensify rainfall, triggering the kind of extreme torrential flooding that has repeatedly struck eastern and southern Spain in recent years. The same underlying disruption, in other words, is capable of producing both scorching heat domes and catastrophic flash flooding, depending on exactly how and where the jet stream happens to buckle. What makes this story genuinely global rather than a purely European or North American concern is a discovery that surprised even the researchers who made it. Scientists studying the Indian summer monsoon, a weather system responsible for delivering the majority of annual rainfall to a region home to well over 1 billion people, noticed that observed monsoon behavior had been drifting away from what climate models predicted for years, and nobody could fully explain why. A research team ran simulations specifically testing whether removing the North Atlantic cold blob from their models would change the outcome, and the results were striking. With the cold blob included, the sharp temperature gradient it creates over the North Atlantic altered jet stream winds and pressure systems across the entire Eurasian landmass, intensifying the jet stream above the North Atlantic and strengthening a separate blocking pattern over the Ural Mountains in western Russia, thousands of miles away from where the cold blob actually sits. That distant blocking pattern, in turn, was found to be reshaping the timing and intensity of the Indian monsoon itself. One of the researchers involved in that study described the finding carefully, noting that this connection represents one of the key building blocks for eventually formulating a complete theory of how these interconnected systems will behave in the future, rather than a fully settled explanation on its own. That kind of scientific caution is worth holding on to, because it reflects how genuinely complex this web of connections is. A patch of cooling water south of Greenland, invisible to nearly everyone who has never studied oceanography, is now being seriously investigated as a contributing factor behind monsoon disruptions capable of affecting agriculture, water supply, and daily life for well over 1 billion people on a completely different continent. Back in the North Atlantic itself, scientists continue debating exactly how alarmed the public should be about where all of this is heading. Some commentary pushes back firmly against the more dramatic framing of this research, arguing that mainstream scientific consensus still treats a rapid AMOC collapse as unlikely without extraordinary triggering conditions, and cautioning against treating an evolving area of ocean atmosphere science as settled proof of imminent catastrophe. That skepticism is a normal and useful part of how scientific understanding gets tested and refined over time. What is much harder to dispute is the immediate, observable link between the cold blob and the disrupted weather patterns already showing up this year. The blocking pattern is not a projection sitting decades in the future. It is a mechanism actively playing out over Europe and reaching into Asia right now, documented through direct observational data rather than speculative modeling alone. Part of what has shifted the tone of this research is the sheer length and consistency of the observational record now available to scientists. 70 years of data confirming reduced ocean heat transport into this specific region is not a short-term blip that could plausibly reverse itself within a few seasons. It represents a slow, sustained trend, one that closely tracks with independent evidence of a weakening AMOC gathered through entirely separate monitoring methods, including a dedicated array of ocean floor instruments that has directly measured current strength across the Atlantic for years. When multiple independent lines of evidence, gathered using completely different techniques, converge on the same underlying trend, it becomes considerably harder to dismiss the pattern as coincidence or short-term natural variability. There is also a forward-looking piece to this story that matters for anyone trying to understand what comes next. Ocean analysts, tracking the cold blob's current extent, report that it is expanding again, with forecasts suggesting the anomaly will persist well into the coming winter season. At the same time, a powerful El Niño event is developing separately in the tropical Pacific, adding an entirely different and much stronger source of global atmospheric influence into the mix. Forecasters studying how these two systems have historically interacted point to a specific, recognizable pressure pattern that tends to follow strong instances of the cold blob. One, that in the past has produced a corridor of unusually cold air stretching from western Canada into the eastern United States, paired with a blocking high sitting over Greenland and a persistent area of low pressure parked over western Europe. If that historical pattern holds again this year, it offers meteorologists an early, if imperfect, signal for what the coming winter might look like across 2 entire continents. None of this means every heat wave or every flood from now on can be traced directly back to a single patch of ocean water. Weather remains an enormously complex system shaped by countless interacting factors. And the cold blob is one significant piece of a much larger puzzle rather than the sole explanation for any individual extreme event. What has changed, according to the researchers publishing this work, is the confidence with which they can now describe the cold blob's role in that puzzle. What was once treated as an intriguing but poorly understood ocean anomaly is increasingly being described as a measurable, trackable driver of blocking patterns capable of reaching across entire hemispheres, from drought and heat over Europe to catastrophic flooding in Spain to disrupted monsoon rainfall across South Asia. For the scientists who have spent careers studying this specific patch of ocean, the accumulation of evidence this year appears to represent a genuine turning point in how seriously the finding is being taken. A phenomenon that used to require lengthy explanation and qualification is now being cited directly by meteorologists, explaining in real time why an entire continent's weather has refused to move for weeks on end. As monitoring networks continue collecting data, and as researchers refine exactly how far this mechanism's influence actually reaches. Expect the story of the cold blob to keep expanding well beyond the borders of the ocean where it was first discovered, and well beyond the borders of the continent that first noticed its effects. To appreciate how unusual this pattern really is, it helps to look at how scientists actually measure ocean circulation strength in the first place, since the tools available today are far more precise than anything researchers had access to even 20 years ago. For decades, understanding the AMOC relied heavily on indirect clues, things like surface temperature anomalies, scattered ship measurements, and historical records pieced together from centuries of maritime logs. That changed with the deployment of a dedicated observation network stretched across the entire width of the Atlantic near 26 degrees north latitude, roughly along the line connecting the Bahamas to the coast of Morocco. This array of moored instruments, anchored directly to the seafloor, continuously measures current speed, temperature, and salinity across the full depth of the ocean. At that latitude, giving researchers something they never had before, a direct, ongoing measurement of how much water is actually moving through the system, rather than an estimate built from surface signals alone. Data collected through this array has shown considerable year-to-year variability, which is exactly what makes long-term trends so important to establish carefully before drawing conclusions. Short-term fluctuations in ocean circulation are normal and expected, driven by seasonal wind patterns, temporary storm activity, and natural variability that has always existed in ocean systems. What researchers have been working to establish is whether the recent slowdown represents a genuine, sustained trend rather than simply another temporary dip within that normal range of variability. The combination of direct current measurements from the observation array, historical reconstructions built from ocean sediment cores, and now the newly published 70-year analysis of heat transport data has moved the scientific consensus meaningfully toward treating this as a real, sustained weakening rather than short-term noise. Sediment cores in particular offer a valuable long-term perspective that instruments alone cannot provide, since they allow scientists to reconstruct ocean circulation patterns stretching back thousands of years by analyzing the chemical composition of material that settled on the ocean floor during different climate periods. Those historical reconstructions reveal that the AMOC has weakened dramatically before in Earth's past, most notably during a period known as the Younger Dryas, roughly 12,000 years ago, when a sudden influx of fresh water from melting ice age glaciers disrupted the circulation so severely that it plunged large parts of the northern hemisphere back into near glacial conditions for over 1,000 years, even as the rest of the planet was warming out of the last ice age. That historical precedent matters, because it demonstrates the AMOC is capable of shifting into a dramatically different, more sluggish state under the right conditions, rather than simply oscillating gently around a stable average. What concerns some researchers about the present-day situation is that today's slowdown appears to be happening without anything nearly as dramatic as an ice age glacier collapse triggering it. Instead, the contributing factors look considerably more gradual, tied to the slow, steady melting of the Greenland ice sheet pouring fresh water into the same region where the circulation's sinking process takes place. A 2024 study led by Marilena Oltmans specifically traced this freshwater influx from Greenland's melting glaciers to the colder surface waters now persisting in the North Atlantic, adding weight to the argument that human-driven climate change is actively contributing to the very ocean anomaly, now disrupting weather patterns across multiple continents. Freshwater is less dense than the salty water surrounding it, and large volumes of it entering the sinking region can interfere with the density-driven process that keeps the entire circulation moving, since that process depends on water becoming dense and heavy enough to plunge toward the ocean floor and begin its journey south again. The ripple effects of a weakening circulation extend well beyond blocked jet streams and disrupted monsoons alone. Fisheries across the North Atlantic depend heavily on nutrient distribution patterns tied to the circulation's normal behavior, and researchers have already begun documenting shifts in fish populations that track closely with the region's changing temperature profile. Storm formation and intensity represent another area of active research, since the same sharp temperature contrasts responsible for bending the jet stream can also influence how storms develop and strengthen as they cross the Atlantic toward North America and Europe. Some researchers have proposed a link between a weakening circulation and changes in hurricane behavior along the eastern seaboard of the United States, though this particular connection remains an active area of ongoing study rather than settled scientific consensus, and researchers are careful to avoid overstating our relationship. Sea level rise along the eastern coast of the United States represents another consequence tied directly to circulation strength that receives comparatively little public attention. A stronger AMOC, through the physics of how moving water interacts with the shape of the coastline, actually helps keep sea levels along the U.S. East Coast somewhat lower than they would otherwise be. As the circulation weakens, that effect diminishes, meaning cities from Boston down through the Carolinas could see an additional circulation-driven contribution to sea level rise stacked on top of the broader global increase, already underway from melting ice sheets and thermal expansion of warming ocean water worldwide. Public discussion of this research has, understandably, split into sharply different camps depending on which outlets people follow. Some coverage leans heavily into worst-case scenarios, framing an eventual AMOC shutdown as a near-certain, imminent event, glossing over the genuine scientific uncertainty that still surrounds the exact timing of any potential tipping point. Other commentary swings hard in the opposite direction, dismissing the entire body of research as exaggerated fear-mongering designed to generate attention rather than reflect careful science. The most accurate picture sits firmly between those two extremes. The cold blob itself is real, well documented, and already measurably influencing weather patterns playing out right now across Europe and Asia. The longer-term question of whether the full AMOC system eventually crosses a genuine tipping point, and if so, when, remains a subject of legitimate ongoing scientific investigation rather than a settled, agreed-upon certainty in either direction. What does appear increasingly settled, based on the growing body of published research this year, is the underlying physical mechanism connecting ocean temperature to jet stream behavior. Researchers across multiple independent teams, studying the problem through different methods and different regional lenses, have converged on the same basic explanation. A sharp temperature gradient in the ocean physically reshapes the air currents above it, and that reshaped air current then determines whether an entire continent bakes under record heat, floods under torrential rain, or watches its monsoon season arrive early, late, or diminished. That convergence across independent research groups, using different data sets and different modeling approaches, is exactly the kind of pattern that tends to strengthen scientific confidence over time, even while individual details continue getting refined with each new study. As monitoring technology continues improving, with expanded satellite coverage capable of tracking sea surface temperature anomalies with greater precision, and with the observation array across the Atlantic continuing to collect direct current. Measurements year after year, researchers expect their understanding of exactly how far this mechanism's influence reaches to keep sharpening considerably in the years immediately ahead. For now, what is already clear is that a patch of cooling ocean water most people will never see or think about has become one of the more closely watched variables in modern meteorology, capable of explaining why the sky over an entire continent can simply refuse to move for weeks at a stretch, and capable of reaching far beyond the ocean where it was first noticed.